So now we can move on to the next aspect of DevOps, which has to do with defending customer data. Security sort of means a lot of things to a lot of people, but we're going to talk about some of the specific aspects of security that you as a developer are able to have some control over in designing your app. And we'll start with talking about SSL or TLS, depending on which acronym you care to use. Our kind of general roadmap for what we're going to talk about, these are sort of some of the most common or prevalent security considerations that you as an app author would have to take into account. We'll talk about SSL and what it does to prevent eavesdropping. We'll talk about SQL injection, which is, these days, I think there's sort of no excuse for that bug because frameworks like Rails have so many good mechanisms that you should be using. And really, SQL injection only happens if you're careless at this point. And then similarly, cross-site request forgery. We will not do lecture content on cross-site scripting, but you can read about that in the book a little bit. But basically, for security, there's things that you as the developer have to worry about, and there's things that the infrastructure provider like Heroku would have to worry about. So we're going to focus on the ones that apply really to the way that you author your app. And we can start with SSL or TLS. So secure sockets layer or transport layer security, depending on which one you want. Really, TLS is just an enhanced version of SSL that fixes a few design implementation issues. But for all practical purposes, we can sort of consider them interchangeably. The idea is very simple. It's that the traffic at the HTTP level is being encrypted, and therefore people who are trying to eavesdrop on the traffic will not be able to see it. And the problem that SSL had to solve was that, in general, to create a secure channel between two communicating parties, those parties have to share a secret that nobody else knows, right? That secret is what is used to secure the channel. So typically, a secret that the two parties might share would be an encryption key that's symmetric. And if nobody else knows the key, then you can use that to encrypt and decrypt the traffic. And of course, the challenge is on the web, the two parties don't know each other. One party is a server that wants to attract users. The other party is a user who has never interacted with that server. So obviously, there's no secret that they can share. And the solution to that problem is tricky enough that, again, somebody won the Turing Award for doing it. Ron Rivest, Len Edelman, and Adi Shamir. And they are, of course, the RSA and RSA security. They got the Turing Award in 2002 for their contributions to public key cryptography. So what does SSL actually do and what does it not do? We start with the idea of the public key and the private key. So a key actually has two matched parts. One part you arbitrarily choose to reveal as the public part that everybody knows and you publish it as widely as possible. The other part you keep private and absolutely nobody besides you know it. And the key, get it? The key relationship between these is that given one of them, there's no practical way to deduce the other one, right? Leaving considerations of quantum cryptography aside. So the main idea is that if you encrypt something with one of them, you need the other one to decrypt, and you can do that in either direction. So how do you use this? One of them is if a message is received and Bob's public key is able to decrypt it, you can infer that Bob's private key must have been used to create it. And so by extension, you can infer that the message really is from Bob, or at the very least, somebody who has managed to steal Bob's private key. Conversely, if I use Bob's public key to create a message, then only Bob can read it, because if the public key is used for encryption, you have to use the private part for decryption. So this is a way for me to create a message that everybody knows the public key. So anybody can create a private message for Bob, only Bob can read it. So how does this work in the context of SSL? If you are a server, let's say Bob runs his server, bob.com, Bob goes to a certificate authority, proves who he is by submitting some ID or whatever other procedure, shows that he has this website that he wants to obtain a certificate for, and the certificate authority uses its private key to digitally sign a certificate that basically says, yes, this site is really bob.com and it really is owned by Bob. So the certificate is really an attestation of something, right? And the way that Bob proves this is, sort of left up to the implementer. The certificate gets installed on bob.com server. And now when a user visits bob.com server, most web browsers have the public keys of the major certificate authorities already built into them. So essentially, the browser is checking whether a certificate exists that is decryptable and valid with some certificate authority's public key. If that is the case, then the web browser can assume that the certificate authority must have created that certificate. Now, of course, there's been a number of famous security breaches where somehow a bad actor got hold of the private key of some certificate authority And then that certificate authority had to basically revoke, essentially invalidate all their certificates and say, somebody got our key and has been creating fake certificates that look like they're from us. But absent a security breach of that kind, the web browser can basically determine that, yes, this server really is owned by the party that says they own it. They do a Diffie-Hellman key exchange, which is basically a simple version of this is the browser will generate a random number, encrypt it using the public key of the remote server, sends it to the remote server, and now we have a secret, right? So now, from starting out with a situation where we didn't share a secret, we've gotten to a situation where we have securely exchanged a secret, and that secret can be used to handle encryption for the rest of the session. And in Rails, really just putting force SSL in your top-level controller basically forces some or all of the actions to use SSL. You can actually have some actions opt out of using it, but these days you need a good reason to do it, right? The way the web is going these days is sort of SSL everywhere, and there's kind of no reason to visit an insecure website. Now, in practice, it's important to realize how force SSL works. It actually causes a redirect to the HTTPS version of that URL. So this is one more reason to have nice RESTful URLs, avoid side effects if you're using GET and so forth, because if somebody tries to do a GET using the insecure version of a URI to your server and you've used force SSL, all that happens is that they're automatically going to get a redirect to that exact same URL, but with HTTPS prepended as the protocol. And so, woe be unto you if the link that they are trying to visit is somehow non-idempotent, meaning if the effect is different of them visiting the link twice than if they visit it once. And so another good reason to avoid side effects on HTTP GETs. So that's the basic idea behind SSL, right? And the simplest way you can think about it is it secures the channel. It makes it impossible, or almost impossible, for an adversary to snoop on all of the traffic going between the web browser and the server, including the HTTP requests, responses, and all the content. But what does it not do? Very importantly. First of all, even though the user can be confident that the server is genuine, it doesn't say anything about who the user is, right? So if the server cares who the user is, it has to do something else, like as we've seen, collect a password or use single sign-on. It also says nothing about what happens to sensitive data after it reaches the server. The data is certainly protected from eavesdropping while it's in transit, but if the server insecurely stores the data, it's possible for adversaries to compromise the actual storage on the server side, and then they don't have to snoop on the data at all. They just wait for it to arrive. It says nothing about whether the server is vulnerable to other attacks. So we're going to show a couple of other ways that a malicious adversary might attack a SaaS application. SSL doesn't do anything really to help with most of those attacks. And certainly it doesn't protect the browser from malware, right? If the server is serving content that exploits a browser bug, whether the server is doing that deliberately or whether the server has been infected using one of these other attacks, SSL will simply deliver the bad content securely, right? So SSL everywhere is pretty common, but don't overestimate what SSL does. The one and only thing it does is protect the data while it is in transit. Everything else has to be mitigated in other ways.